Thank you very much for the invitation. I'll be presenting some joint work with Benny Sudakov and Istvan Tomon, and I'll be talking about subgraphs, which on the one hand will be small. They will span a small number of vertices, but on the other hand, they will be fairly dense in the sense that they will have large average degree. And I'll be presenting some results about the existence of these subgraphs. So I'd be very happy if you ask questions during the talk, if anything needs clarifying, or if you have any questions. Okay, so I'm already having some. Good. Perfect. So what's the motivation? One motivation comes from theoretical computer science, where it's an important problem to design an algorithm which finds the subgraph on a fixed number of vertices, say k vertices, which has the most edges. So, because the number of vertices is fixed, most edges means largest average degree. This is known to be a very difficult problem, and it's NP hard, and it has no polynomial time approximation scheme if you make some complexity theoretic assumptions. And the best polynomial algorithm achieves an approximation up to a factor n to the 1/4, meaning that the subgraph, the density of the subgraph that it finds, compared to the optimal density, may be off by a factor n to the 1/4. And this problem led Feige and Wagner to pose a different question, more extremal graph theory flavor question, which is this problem that I will be talking about in this talk. So given a graph whose number of edges and vertices we know, so we know what the number of vertices is, it's always going to be n, and we know the number of edges, but we encode it as the average degree. So we know the average degree as well. And we want to find a subgraph of average degree at least some constant s, so average degree at least 100. How small a subgraph can we take? How small a subgraph must there always exist with this large average degree? So how small can T be such that we can always guarantee the existence of a subgraph on atmos T vertices with average degree at least S? So just to give an example, let S be 4 and let D be n to the 1/4. So everywhere in this talk, you should think of the average degree D as average degree of the host graph D as an arbitrary function of n, say in this example n to the 1/4, but S, the average degree of the small subgraph that we are aiming for, is always going to be a constant. So in this example, 4. So we are trying to find a subgraph, a small subgraph of average degree at least 4 in the host graph, which is average degree n to the 1/4. How small can the small subgraph be? If we take, so one way to find a small subgraph is with large average degree is to take as a random subgraph. So if we take a random subgraph on T vertices, will that work? So the expected, so originally in the graph, the average degree is D. If we take a random subgraph on T vertices, then the average degree will become about T over n times D, which is T over n to the 3/4. And we want this average degree to be bigger than S, so we certainly want T to be at least about n to the 3/4. That means that with this strategy, the best T we can guarantee is about n to the 3/4. So this strategy will show that we can find a subgraph on n to the 3/4 vertices with average degree at least 4. But there is a better strategy, we can do a lot better than this, which is basically the content of my talk, but of course in a more general, for more general parameters. But in this particular example, we could take t to be as small as n to the 1/2. So we can find a subgraph and only n to the 1/2 vertices, which still has average degree at least 4. And the results, so the bounds on the size of t that we obtain will be optimal up to polylogarithmic factors. So this, in this example, this n to the 1/2, for example, is the tight exponent. It's 1/2 is the right exponent. So which results are known? So the case s equals 2 is a little bit different than all the other cases, because if you find a subgraph with average degree at least 2, it necessarily contains a cycle. It necessarily contains a cycle. On the other hand, a cycle itself has average degree 2. So the problem in the s equals 2 case just becomes find a cycle as short as possible. So how short a cycle one can guarantee in a graph with n vertices and average degree d. This is a famous problem. This is well studied, called the girth problem. And the answer is known up to a constant. It's known that it's roughly log dn, meaning that you can always find a cycle that has length at most log dn, but there are examples where you cannot find a shorter one. Now, as I said, this s equals 2 case is a little bit different than all the other cases. So let s be greater than 2 now. In this case, the lower bound observation of Feige and Wagner is that there are graphs in which you have to take your set to be of size at least n times d to the minus s over s minus 2. You see that the thing is not even defined for s equals 2, so something clearly is going on there. But for s greater than 2, this is a valid lower bound. There are examples of n vertex graphs with average degree d in which every subgraph of large average degree must have order at least this n times d to the minus s over s minus 2. And this is the number. It's perhaps helpful to remember it. I will write it down a number of times later, but this is the number we are aiming for. This is what we will prove, that this number of edges is essentially sufficient to find a subgraph with large average degree. Yeah, so this observation was just by using random graphs. And they conjectured that this construction is tight, that this bound is tight to polylogarithmic factors. So for basically for the whole range for which this question makes sense, so s is greater than 2, d has to be greater than s just because if the entire graph has average degree less than s, then perhaps no subgraph has average degree more than s. So then it's not a question about how small you can find it, but you just cannot find any subgraph perhaps with large average degree. So d bigger than s certainly makes sense. And if d is bigger than n, this n to the s minus 2 over s, then the right-hand side in this bound becomes more than n. So again, doesn't make a whole lot of sense, because we are trying to find the smallest subgraph, but if the bound is more than n, then it's a meaningless. Sorry, no, I'm saying it wrong. N to the d minus s over s minus 2 becomes less than 1, so the right hand side becomes less than 1, and you clearly can't find a subgraph, a large average degree subgraph on fewer than one vertex. So it's really the this range is the entire meaningful range. And this you might wonder about this logarithm factor. Is it necessary? It wasn't present in the lower bound, but actually you can modify the lower bound such that the logarithm factor is also necessary, at least when d is about this n to the s minus 2 over s. So the log is needed also for some values of d at least. So the conjecture would say that you can always find a subgraph with at most this many vertices, which has average degree at least s. Now, Feige and Wagner obtained some approximate versions of their conjecture, and they focused on the case where s is about 4. Now, they showed two things. First, if you don't want average degree at least 4 exactly, but you're happy with average degree at least 4 minus epsilon for some constant epsilon, then this number of edges is enough. So if you plug in s equals 4, you would get n times d to the minus 2. So n times d to the minus 2 is what you would want to get for s equals 4. And they get that, but not for s equals 4, but for s equals 4 minus epsilon. So they get the right number of vertices, but a slightly smaller average degree. And they have another result in which they get average degree 4 exactly, the second result, but then they need to use more vertices. Then it's not enough for them to have n times d to the minus 2 vertices. They need n times d to the minus 1.8 vertices. So this is two approximate results. And Alon and Hod also had similar approximate results for some values of s and some values of d. And our contribution is a complete answer to this conjecture, is a positive answer to this conjecture in a slightly stronger form, in the sense that our logarithmic term is actually logarithmic in d. So when d is small, then that actually improves the log n bound. So this is what we show. In other words, we show that in any m vertex graph with average degree is d, there is a subgraph on this many vertices which has average degree at least s. So we can find small subgraph with large average degree. Now, you might wonder what happens if you want a really small subgraph with large average degree. So you don't just want subgraph on this many vertices, but you want actually a subgraph on a bounded constant number of vertices. Then clearly the question is, how large average degree do you need to start with in the host graph? And the observation is you have to start with something strictly more than n to the s minus 2 over s. Because if you just start n to the average degree n to the s minus 2 over s, then there are examples which do not contain subgraphs on a bounded number of vertices with average degree at least s. That's again just a simple random graph construction. And it led Verstraete to conjecture that that is enough. So once you have n to the s minus 2 over s plus epsilon average degree, then you can find a subgraph on a bounded number of vertices with average degree at least s, where how small the subgraph is depends on epsilon, of course. It follows from the previous observation that it has to depend on epsilon. So this conjecture was proved for integer values of s by Jung and Newman, and we proved this conjecture for all values of s. So what I want to do in the rest of the talk, first I will give some ideas about the proof of not this result, but the previous one. So the one with this specific bound on the size of the small subgraph. And then I'll mention some interesting open problems, I think interesting open problems related to this. So proof ideas. So how do we construct a subgraph which has small number of vertices but lots of edges? That's really the question. For the moment, we can forget about the exact dependence of this exact formula. For the moment is not important because we are trying to just go through the ideas, but how do we construct? And the idea is to take some tree, define a tree, which is fairly big. It's not as small. It's not a constant size tree. It's a big tree. And you find a lot of trees in your host graph, which all have the same set of leaves. So you find a bunch of trees. I'll have a picture on the next slide. Perhaps it's good to show it now. So you have 4 trees, these binary trees of depth 2. You have 1 of each color, and they all share the same set of leaves. This set of 4 leaves is the same for every color. So that's kind of the strategy. We glue together, we find a bunch of trees sharing the same set of leaves, and we somehow will argue that on the one hand, the number of vertices spanned by these trees is not that large, but the number of edges is quite large. And very intuitively, the idea is that every time you add a new tree, you add a number of new vertices and a number of new edges, but the leaves are already there. So the only new vertices that you add are the non-leaves. But you add all the edges of the tree. If I take a tree of another color and add it to this picture, I'll add 6 new edges, but only 3 new vertices because the leaves are already on the picture. So what kind of will matter is how many leaves the tree has compared to the number of vertices it has. So we now have to somehow carefully choose this tree so that the number of edges or vertices, they just differ by 1, these 2 numbers. Number of edges or vertices will be about this target size, this n times d to the s minus s over 2. And the number of leaves will be a constant proportion of this. So it's going to be s minus 2 over s times t. Intuitively, when s is large, then this s is very close to t. So if s is large, then almost all vertices will be leaves in the tree, which is that when you take a bunch of trees with the same set of leaves, every new tree will introduce very few new vertices because only the non-leaves will be the new vertices. So you'll have a ton of new edges, but very few new vertices, meaning that the graph will be fairly large, fairly dense. So larger the S is, the more leaves we use. Okay, and we take a tree with T edges and L leaves, and our goal is to find many copies indeed, so many copies sharing the same set of leaves. And we take the union of some of them. I'll explain a little bit how we take the union. I mean, there is this issue that on the picture, it was very nice that everything was disjoint from the previous thing. That's absolutely not guaranteed. If you take 2 trees, or 10 trees, which have the same set of leaves, they could overlap in many different ways, making it very difficult to say something about the number of edges that they have in total and the number of vertices they have in total. So that's a problem. But let's not worry about that for now. And this vertex set spanned by the union of some of these trees will be our small candidate for a small set of large average degree. So this was the picture. This was what we are trying to do. And now I just want to mention, summarize what I basically already said. Assume we have a very large constant number of copies which are edge disjoint. So for now, we make this assumption that they are edge disjoint. Copies of the tree sharing the same set of leaves. And we take R to be the union of these trees. Every new copy of the tree adds as many vertices to this picture, as many non-leaf vertices the tree has, which is 2 over s times t. Every new copy of t adds 2 over s times t non-leaf new vertices. And every new copy of t gives t new edges, because every edge is new. If you do that for a long time, you will get average degree very close to s, because you get t new edges every time you get 2 over s times t new vertices. So you can convince yourself, if you do that for long enough, you'll get average degree approaching s. So that's the strategy. That's the strategy. Now, there are things to check. I mean, first of all, the key thing, the heart of the argument is that there are many trees on the same set of leaves. I've said that I choose many trees with the same set of leaves, but why do they exist? To argue that they exist, I need to argue that there are many trees in the graph, and there are more copies of this tree in the graph than there are sets of possible leaves. Then it's a pigeonhole. If there are 1,000 possible sets of L leaves, but 10,000 trees, then there will be 10 which are in the same sets of leaves, on the same set of leaves. So can we get a good lower bound for the number of trees? And here I'll again first cheat and then later explain how you can get rid of this cheating assumption. So the tree has t edges and a host graph has average degree d. Now, if the host graph is anything like a random graph, then I claim that the number of copies of t is about n times d to the t. Because if you choose the first vertex of the tree in n ways, you map it to anywhere in the graph. And then every new vertex in the tree, you already have chosen one neighbor. I mean, if you imagine the most natural orderings of the tree, you always have, when you take the next vertex in the tree, it has one neighbor already accounted for. And in the host graph, that leaves d options, because if it's a random d regular graph, then you have about d options to continue. So you get roughly n times d to the t copies. And the number of possible choices for a set of L leaves is n choose L. That's just obviously true. So what we need to check is that n, this number of trees, is bigger than this number of possible sets of leaves. And now we just plug in what these values were. And n choose L is estimated by this usual formula. We plug in the formula for L in terms of t, and then we plug in the formula for n. Not super interesting to go through the computation, so I'll just leave it like this. N choose t is at most d to the t for these parameters. And that means that you will indeed have many trees with the same set of leaves. That's good. So the heart of the argument does work. And we do understand why we get exactly this answer, this t. I mean, we now understand why this is the answer, but it remains to check some details of our argument. We did cheat a number of places, so let's address those. What are the problems? What were the problems with this sketch? One of the main problems was that these trees we took, there are many trees with the same set of leaves, but they don't have to be edge disjoint. So in their union, if some edge appears more than once, we double counted or triple counted an edge. And we don't have as many edges in the union as expected. So the average degree might be lower than we expected. You might say that, okay, but then if two trees have the same edge, then also they have the same vertices. So if the number of edges is smaller, then the number of vertices is also smaller. So maybe the average degree is still okay. But let me show you an example which shows that that's not necessarily the case. So if you start with this tree, which is the black one, so just ignore the colored edges. Just look at the black tree. So it's a tree with 8 edges. Yes. Now, if I take 3 copies of this tree, one is the black and one is the black, but with the blue replacing the top vertex, and one is the black, but with the red replacing the top vertex, then you get 3 trees with the same set of leaves. And the problem is that when you introduce these new colors, you get one new vertex and 2 new edges, which is a ratio of 1 to 2. But if you got a genuinely edge disjoint one, then you would get 8 new edges and 3 new vertices. So you would, with the edge disjoint situation, you would get 8 over 3. Here you only get 2 over 1. So you get actually a verse proportion of edges compared to vertices. So if you do this, and if this thing happens, you will end up with a smaller average degree than you expected. That will break the proof down. So this tree is something we can't use. So what we'll do is we'll use some specific trees. All we needed so far about the tree is that it has a given number of edges and a given number of leaves, but I didn't need anything about their structure, but now I will. Now I will introduce a class of trees which will be better for us, a class of trees which we'll call balanced, because they won't have this property that there is a part where the tree is kind of very sparse. So here the problem is that the top part is very sparse, that the top vertex only is adjacent to 2 edges. So if the top part is repeated many times, or rather, sorry, if the top part is new many times, but everything else is repeated, you get a smaller number of edges compared to the vertices. So we need a tree which is more balanced than this. And perhaps slightly complicated looking definition, but really I'll just explain what it is. So a balanced tree is a tree which doesn't have a part which is sparser than the rest. So for every subset of vertices, of non-leaf vertices, you define ES to be the edges touching S, and this ES over S is then the ratio of edges touching S divided by the size of S. So it's kind of the average degree of vertices in S. And if we assume we call the tree balanced if this average degree around this local average degree in S is always at least as big as the global average degree of the tree. So in every small part, you are at least as dense as the entire thing. And if you have this property, then if you take a union of these trees with the same set of leaves, you must have large average degree, as expressed by this lemma of Book and Conlon, who showed that in any union, the number of edges is large compared to the number of vertices. And this is the same inequality that you would get. This is the same inequality that you would get if you took edge disjoint copies. So it's not super important for you to look at this inequality and understand where exactly it comes from. It's just the same inequality that you would get if you had edge disjoint copies of the tree. So for balanced trees, even if they are not edge disjoint, we get the same average degree that we would get if they were edge disjoint. So that's great, but do these exist? Yes, fortunately they do. It's another lemma of Book and Conlon. They prove that for any TNL, these exist, which is exactly what we need. For any number of edges and any number of leaves, you can construct such a thing. And one family of examples are some caterpillar graphs, meaning that caterpillar graphs means there is a path, this top path, and there are leaves hanging from it. So it looks like a caterpillar where these leaves are the legs, I guess. So these are constructions of these bands. You can see from the picture it's reasonably balanced. Like there's no part which is much sparser than other part. Because you have to check the definition. Okay, that's good. So that resolved this issue. There was one other issue which I want to address, which is that I claim that we have many copies of the tree in the graph. If the graph is random-like, if the host graph is random-like, then we have this lower bound for the number of trees, for the number of copies of T. But I didn't say anything about what if the graph is not random-like, and there could be issues. So it actually can even happen that there is 0 copy of T in our graph, because G could be a disjoint union of cliques of size, say D. So you have clique of size T, clique of size D, clique of size D, disjoint union of these. This graph has average degree D, because every vertex has degree D, but it does not contain any copy of the tree if T is bigger than D. If our tree has size bigger than D, then the tree just doesn't fit in any of these cliques. So we look at 0 copies of T. That's a big problem because we need lots of copies. However, our ultimate goal is to find a small subgraph of large average degree. And in this example where the graph is a disjoint union of cliques, every clique is extremely dense and quite small. So you can just use any clique or subset of clique. So this is what we will exploit here, that either we directly somehow find a small subgraph of large average degree, or if we cannot, then the graph must have some property which I'm about to explain, guaranteeing that you have many copies of the tree. And the property, I mean, it's a graph theoretical notion, it's called expander graphs. So either the graph is a good expander, which I'll explain what it is. If it is a good expander, then it will contain many copies of the tree. If it's not a good expander, I will show that it has a small subgraph of large average degree. So what is an expander? An expander is a graph in which every subset, for every small subset, if you look at the set of neighbors, it's very large compared to the set itself. So it kind of expands. If you look at the set and its neighborhood, the neighborhood is much bigger than the set itself. So to quantify this is an MK expander if every set of size at most M expands by a factor K, meaning that the neighborhood has size at least K times the set. So the set expands if it looks something like this. On the left-hand side there is this S set. The right-hand side is neighborhood, which we denote by gamma S, which is assumed to be much bigger than S. So if this holds for every S, every small S in the graph, then it's a good expander. It's an MK expander. If it holds for every set of size at most M. So now I want to tell you that I want to explain why it's the case that if it's not an expander, then we have a small subgraph of large average degree. And it's kind of not too complicated, because if it's not an expander, then that means that there is a set whose neighborhood is small. There is a set S, which is small, whose neighborhood is also small, but a set and its neighborhood together contain every single edge leaving the set S. Every edge leaving the set S is between S and the neighborhood. So if both S and the neighborhood are small, then it's a small subgraph which contains a lot of edges, because it contains every edge leaving S. So if the original graph had some decent minimum degree, then you will get a very big average degree in this small subgraph. So to be more precise, if G is not an MK expander, but has large minimum degree, then it contains the subgraph on at most k+1 times m vertices with large average degree. Because of what I said, because you take a set which certifies that it's not an expander. So you take a set for which the neighborhood is small, and then the union has size only k+1 times s, and it contains every edge leaving the set. So it will have large average degree. And what do you do if J is an expander? If G is an expander, fortunately, we have a classical result, which says if G is an expander, it will contain every tree. And we can even modify some arguments here to say that we find many copies of the tree. So if our graph is an expander, MK expander, we can find our tree, our large tree, and we can find many of them. So whether or not the host graph is an expander, we are happy. Either by, if it's not an expander, we directly find small subgraph of large average degree. If it is an expander, we find many trees, and we run the argument that I had talked about before, with the tree is sharing the same set of leaves. So that's all I wanted to say about the proof. And now I want to mention a few open problems. So one very natural one, a very nice one, I think, is the minimum degree analog of our result. So our result finds a small subgraph of large average degree. But what if we want to find small subgraph with large minimum degree? That should be somewhat harder, of course, because maybe the average degree is 10, but the minimum degree is less than that. So what is, and it's a question that had been considered already by Erdős in 90s. So it's definitely something people care about. So how small can the subgraph be? And no, you might say that, okay, well, if you find a subgraph with average at least 2s, then in it there exists a subgraph with a minimum degree at least s. This is a somewhat folklore graph theory result that every graph with average degree at least 2d contains a subgraph with a minimum degree at least d. So you can pass from average to minimum by losing a factor 2. So that means that our result gives some bound, but we are very certain that that bound would, this approach is not optimal because it loses something. Instead of 2s, we get just s. And the random construction, the best known construction is still just the random construction. So we actually think that the answer should be the same. The same number of vertices that guarantees average degree at least s should in fact guarantee minimum degree at least s. But our approach doesn't work because these trees that you glue together, while they will have average degree s, they will not have a minimum degree s. There will be vertices of smaller degree. So we do think the answer is same, but we can't prove it. And there is even a stronger requirement that one can hope for. So one may even ask for a regular subgraph. So not a average degree s, not minimum degree s, but an s regular subgraph. Obviously, s is now an integer. And we still think that the answer should be the same up to one caveat, which I'm about to mention. That this is the conjecture. It's just the same conjecture as before, that there should be an s regular subgraph on at least this n times d to the minus s over s minus 2 times log n to the c vertices. So the same number of vertices we were allowed to use before. There's one change. Previously, D just had to be bigger than S. And now I'm saying that D has to be bigger than log n. So what happens if D is less than log n? What happens if the host graph has average degree less than log n? It turns out that there are examples of such graphs which do not have any S-regular subgraphs, let alone S-regular subgraphs in a small number of vertices. So it's a very important example of Piper, Rödl, and Semeredi, showing that there are n-vertex graph with average degree less than average degree close to log n, which do not have an S-regular subgraph, or any S, at least 3. And if they don't have an S-regular subgraph, they don't have a small S-regular subgraph either. So that's a problem. So therefore, we need to assume that D is at least log n. It was proved quite recently by myself and Benny Sudakov that average degree condition, D at least log n, is sufficient to find an S-regular subgraph. But our approach doesn't say how small that subgraph is. So we know how to find an S-regular subgraph, but we don't know how to find a small S-regular subgraph. An S-regular subgraph that's as small as this bound. And finally, what if you want to find a bounded size S-regular subgraph? So you no longer allow this many vertices, just a bounded number of vertices. Then what should the average degree be? And here the conjecture is this, that the same average degree, that's enough to find average degree S, a subgraph on at most T vertices with average degree S, in fact suffices to find an S-regular graph on at most T vertices. So this is a conjecture which previous conjecture may or may not be true, but this conjecture I strongly believe in because it is known for all even values of S and for S equals 3 as well. So in this last conjecture, the only open cases are the odd values of S greater than 3. So there's strong evidence that this is true. And this is actually all I wanted to say. I'm very happy to take some questions if you have any.
Okay, thank you very much. So indeed, are there any questions from the audience? Well, that doesn't seem to be the case. I will stop the recording.